Keynote speaker. Dr. Chen's a professor at the School of Environment, School for the Environment at University of Massachusetts, Boston, and the 2024 recipient of the prestigious Ramon Margal Award for Excellence in Education, a graduate of Harvard University and Scraps Institute of Oceanography. Dr. Chen has dedicated his career to understanding coastal ecosystems and training the next generation of environmental scientists. What truly sets him apart is his passionate commitment to blending scientific research with innovative education. From developing coastal sensor networks to leading transformative projects like Coastal Ocean and the Watershed Integrated Science Partnership. As an expert in both coastal carbon cycling and science education, Dr. Chen brings the perfect combination of scientific rigor and educational innovation to help launch our Massachusetts K-12 Climate Change Challenge. Please welcome Dr. Chen.
Morning.
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 How's everybody doing?
Great.
Good, good. Just trying to see things.
Sorry, I forgot to do my job.
Thank you so much for coming this morning. We're talking about climate change challenges and didn't really know what to expect, but I think some of the things in here will give you some ideas, inspiration, tools to be thinking about what we're going to do, what you're going to do today and throughout the year. So my name is Bob Chen. I'm at the School for the Environment at UMass Boston. I've been there 32 years. I've done a lot of work with Boston Public Schools and teachers throughout the state and the country. And I have a new title called Director of Grand Scholarly Initiatives. It's about thinking about transdisciplinary across departments, across disciplines at the university. And there's no larger challenge and grand scholarly challenge than climate change. It's the existential crisis of our time, and we need everyone to be engaged, involved, particularly the youth. And Jim, thank you so much. The youth are really a loud voice for environmental issues, and they can move the behavior of adults. We have had some students that created a net zero community in a week, touring around Massachusetts, and they presented to the public at the Museum of Science under the giant Earth globe and really engaged people in what their vision was, and people listened to that. I'm thinking about three things. One is that systems are complex and people have hard times understanding systems, but it is one of the NGSS cross-cutting concepts. It's really maybe the most important one. And there are many ways to get into talking about systems, and so I'll give you a few of those. Then the whole idea about how do you communicate the really complex, giant, scary nature of climate change in ways that are simple and engaging for different audiences. And then maybe a few ideas about what kids can come up with for solutions. I'll give you some examples of ways sort of into that. This is a project here called Cool Science, and your students can enter this. It's open. I think the deadline is in January. Coolscience.net is the website, but they create posters about climate change in response to challenge questions. We take the winning posters and put them on buses, public buses on the Queen side, 20 feet long, and educate adults. And we survey the bus riders, and there's a statistically significant increase in their content knowledge about the science after they view the posters. So it works. Pretty simple messages. So they're taking complex science that they learn, they're communicating their science in simple ways, and sometimes there's really simple messages and solutions in these. Climate change leads to more intense storms. We know from this summer the hurricanes are larger because oceans are warmer, at a threshold of 80 degrees. If they're under 80, no hurricanes. Over 80, more hurricanes. Over 80, all over the place, hurricanes everywhere. And they're actually rotating in the correct direction, so the students actually know the science quite well. Don't feed the storms, reduce your carbon footprint now. It's a pretty simple message from the youth. It's not, oh, you gotta listen to the uncertainty or the projections or the whatever. Just stop doing it. You're feeding storms with carbon, with CO2. Pretty simple solutions here. And there's some of the kids in front of one of the buses. So I'll start with this idea about complex systems. We have systems everywhere. There's the human body system, the solar system, the sewage system, and there's different characteristics of each system, which you can have them think about. I do sort of whole workshops on this. Where does the energy flow? You can always ask how the energy flows through something, and you learn a lot about it. You see that there are systems and subsystems and components and connected pieces of it. And that's really important to sort of think about, the interacting elements. And then oftentimes there's a function within a subset and a function among the whole thing. And sometimes there's little loops and things around there, right? So I usually start with an orange. This is a system. And you say, well, why does an orange exist? Well, it exists to have a seed and deliver it so that the next tree can come, but it has a rind that does the protection part. Protects from insects and drying out. It has the segments that isolate from damage the seeds. It has the cells. So you can just open up, I usually spend about an hour with kids opening up, or teachers, opening up an orange and talking about the subcomponents, the interactions, where's the energy flow, where's the mass flow, where's the water come from, where's the sugar come from. Oh, we need leaves, that's photosynthesis. That's a different subsystem of the tree system. So they're connected, but they're subsystems, and you can talk about that. So all of these things are really engaging for thinking about systems. And there are many systems in your and your students' lives. The coffee pot. There's an electrical part. There's like a reservoir. Where's the water come from? What does the coffee do? Why is there a change in color? There's the cell phone system. Students seem to know about these. There's a battery system, an energy system. It's not completely enclosed. You have to plug it in. People know that, right? There's a visual system. There's a sound system. So all of these little components, you can see how the energy flows, where the matter comes, what have you. That climate system sometimes can look pretty complicated. And there are thousands of scientists looking at each one of these arrows and each one of these reservoirs. And you go, well, I can't teach that. It's too complicated. But you can start with systems and say, oh, there are actually some really simple pieces to this. The human body system is incredibly complicated. There's pieces in here and diseases that I can't pronounce, but there's some pretty simple things that I can think about. What can I measure to think about the health of the system? So we talk about emergent indicators. It's a term I sort of made up. An emergent behavior is something that comes out of a system. It's something that happens, like I can do work, I can give a talk. It emerges from this human body that I have, right? And the climate system also does things. It makes currents go. It makes temperatures at different places. An indicator is something that you can actually measure. I'm going to send my students to the pond and measure the water temperature. I'm going to go look at satellite data and look how green a forest is, something like an indicator. An emergent indicator is something that comes out of the system that you or your students can measure. 98.6 degrees Fahrenheit, what does that mean to you? If it's your body temperature, and it's 98.6, I'm not even thinking about the complex system. I'm fine. I'm healthy. Don't worry, nothing's changed. That's what it should be. If it's 102, I don't know what's wrong, but something is wrong with the system. It's a measurement that gives you an indication of some of the function in the system. Thoughts or questions about that? Trying to make a really, really complex climate system something that is tangible and easy to think about. So the Blue Hills Observatory is right here in Massachusetts. It's the oldest, longest continuous temperature record in the United States. It's here in Massachusetts. It's where the American Meteorological Society started. And you might not know that, but there's a guy who measures temperature 3 times a day, every day for the last 120 years. It's not the same guy. They do change every 30 years or so. And it's not a sensor, it's not a satellite, it's a thermometer with mercury in it. It's the same thermometer. He just goes and he reads it and says, 100 degrees, 32.3 degrees. And he does it at 3 times during the day, and he records this in a little notebook that now types into a computer. And the black bars is the 100-year average of mean temperatures at each month. So you take the temperature every day, you do it for the month, you average over the month, and the black lines are the 120-year average of the entire thing. And of course, we haven't finished November, so there's no data yet. It gets updated every day. The red or blue lines, and I don't see any blue ones this year, are the average temperature of this year, 2024. And in every month of 2024, the average monthly temperature is hotter than the average monthly temperature for the last 100 years. That makes sense? And it's not some faraway place. It's a place that you can go. You can hike up to the top of the Blue Hill here in Massachusetts and meet the guy who just reads a thermometer. It's an emergent indicator of the climate system that's available to you. And if you can't go there, you can tell the same story I'm saying. There's a guy. His name is John, or whatever. Okay. So that's great. That's saying that this is a hot year. That's all it's saying, but it's really tangible. If you do this every year, over the last 100, this goes back to 1830, this is the average for the year. So you take all those monthly temperatures, you average them, and yes, temperature is variable, weather is variable. Some years are warm, some years are cold by 2.5 degree average. That's huge. Some years are warm, some years are cold by 2 degrees. This one's a hot one, this one's a cold one. We have El Niños, we have whatever. Oh, I remember that winter. Okay. The coldest year in this decade, even given all of that variability, is warmer than the warmest year 100 years ago. You can't, the weather has fundamentally changed. The climate has changed. We can't get as cool as it was 100 years ago, even with the variability. That means that we have fundamentally warmed at this location in Massachusetts. And this is true of most of the temperature records in the world. Not all of them, but most of them are fundamentally separate. There's some indicators that you might not think about that are indicating climate change. There's another guy named Don who walks up there, does the education programs, he's a great guy, and he walks up the hill every day. And he looks for the first ripe blueberries in the season. And the average date of that is June 21st, over the record that they have going back to 1900. 1900. And you just go, well, it's a ripe blueberry, I'm going to eat it. I mean, you know when you want to eat a blueberry, right? The earliest time now is June, okay, what is this here? June 5th. That means that the ripe blueberries are getting there earlier. Why? Well, the plants know when it's warm enough to be ripe and fruit, and the date of the plants has gotten earlier because the climate has changed. It does change from year to year. Some are warmer years and cooler years, but you watch that the average back here is different than the average here. So there are things in your neighborhood, in your school, in your community, that given a record, you can see the change. The climate change shows up everywhere. Every ecosystem, every neighborhood, everything. And it takes a little bit of student ingenuity sort of to measure that. Maybe they start a long-term record, maybe they get a historical record and it doesn't have to be data. It could be observations in newspapers or the biggest storm, though, whatever. Oh, I haven't seen snow in the last 2 years. It's never happened before that we've had 72 months or whatever it is, 56 months or whatever it is, that we haven't seen 4 inches of snow. I mean, it's been remarkable. That's a different kind of indicator of climate here. There's another indicator of climate change, which is the driver. And this guy is David Charles Keeling. He was a professor of mine at Scripps Institution of Oceanography. And he was a graduate student when he had his advisor say, you know, I think CO2 is going up because of fossil fuel burning, 1956. So maybe you should measure it for your PhD. And he said, well, if I'm going to measure it, I'm going to Hawaii. So he went to Mauna Loa, a very tall mountain in the middle of the Pacific, without a lot of variation of plants breathing in and out every season and whatever. He wanted a very consistent record, and he measured his first thing out there. He took an evacuated 1-liter glass flask, had no air in it, and he went, and he opened it up, and the gas came in, and he closed it, and he brought it back to Chicago and measured the CO2 in it. Why did he hold his breath? Because he could contaminate the sample by breathing out CO2 or breathing in oxygen while he did that. So he wanted to make sure he had a sample that was isolated from the local interferences, his breath and trees, etc. And then he watched it go seasonal wiggle down in the summer when CO2 is being sucked into leaves, back high in the winter when CO2 is being emitted by the degradation of the leaves, and it went wiggle, 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 and it went up, 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 up to 2024, where this is 320. If he had started at the normal interglacial, it's 280. Ice ages is 180. It's always been 180 to 280, 180 to 280 every ice age for the last 2 million years. We went above that, 315, 420. Fundamentally changed the emergent indicator of the climate system, the driver of the climate system, CO2. Just a measurement, and now we have CO2 measurements all over the world that are all going up. Their seasons are reversed in the southern hemisphere, but also wiggly, and less wiggly because there's fewer plants. The wriggles come from terrestrial plants more than the ocean. We can measure why that's going up. CO2 emissions are going up mostly because of the gray. Fossil fuels are literally that. Old carbon that has been photosynthesized to plants, usually, dinosaurs if you believe the Argo commercials, and go into marine systems or peat bogs and sit there and change their chemical composition to something that's incredibly valuable. This very transportable, relatively safe energy source that's not infinite. But we can move it around in cars, we can move it around in trucks, we can move it around in boats as coal or petroleum or natural gas, and we can use it to increase the standard of our living. We can turn on heat in the winter. We can live in really cold places. We can live in really warm places. We can live in dry places and create water with wells. And so the energy has really improved the standard of living for about half the population of the world. So the other half, unfortunately, has been left behind. So that's the fossil fuels. We've also done a lot to the land. We've cut down forests and put in farms. And so in taking that, we've cut down storage of fossil fuels as tree carbon, and we've burned it normally to CO2, which is accumulating in the atmosphere. But, did I miss a slide? But we have another big idea. So one is conservation of energy. We talked about energy flow through things. Another is conservation of mass. So if the mass is coming, we're digging it up from the ground, millions of years old carbon that used to be plants, and now we're putting back the CO2. It's got to go somewhere. And so it took a lot of years to really get a pretty good handle on this. We know that it goes in the ocean. If you put more CO2 in the gas phase, there's pressure that pushes the CO2 dissolved into the ocean, and that causes ocean acidification, right? We know how much is going into the atmosphere. We just measure it, the CO2, like Keeling did, and we can see, so that's the blue is the ocean, the light blue is the atmosphere, and the rest we finally figured out, it's quite variable, goes into land. Turns out if you do an experiment and you grow a plant in double the atmospheric CO2, it grows 30% faster. Even if CO2 is not limiting, water might be limiting, or nutrients, fertilizer might be limiting, the CO2 pushes into the plant and it grows faster. So the trees have acted as a savior to us to take a bunch of the CO2 out of the atmosphere and stick it into the soils or into the wood mass, even though we're cutting down the trees. And this year was the first year on record that the trees had a zero sink. So maybe we've shut off the sink. And that's really catastrophic because then all of the green will become light blue. It'll be more CO2 in the atmosphere than we think, than the models predict. And that's probably because we've had multiple stressors on trees, acid rain, cutting them down, drought, fire, climate change, other things. Trees are not growing as healthily as they used to. So this idea of conservation of mass, really, really important for thinking about all of this stuff, but there's some really simple ways of doing it. And one of the ways is I always bring this little thing.